Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the intellectual ferment of early 19th century Manchester, a city swelling with the energies of industrial and scientific revolution, the foundations of modern chemistry were being quietly and methodically laid. Within this milieu, John Dalton, a diligent Quaker natural philosopher, pursued lines of inquiry that would permanently alter our conception of the material world. His 1805 memoir to the Manchester Literary and Philosophical Society, bearing the unassuming title on the absorption of gases by water and other liquids, stands as a seminal document in the history of science. This text, ostensibly a focused investigation into a specific physical phenomenon, in reality served as the principal vessel for the public unveiling of his atomic theory. It represents a masterful transition from meticulous empirical observation to a grand, unifying theoretical framework, demonstrating how a narrowly defined problem can unlock a universal principle. The paper's genius lies in its logical architecture, moving from the observable behavior of gases in solution to the invisible, quantitative reality of atoms, thereby furnishing chemistry with its fundamental unit of measure and its modern conceptual grammar. The scientific landscape Dalton inherited was one of immense progress and lingering ambiguity. The chemical revolution spearheaded by Antoine Lavoisier had overthrown the phlogiston theory, establishing a new nomenclature and a rigorous emphasis on the conservation of mass through the use of the balance. Chemists could identify distinct gaseous substances, or elastic fluids, and analyze their role in chemical reactions with unprecedented accuracy. Yet, the physical nature of these gases, particularly when they mixed or dissolved, remained a subject of profound debate. The prevailing explanatory paradigm was split. One school of thought, championed by influential chemists like Claude Louis Berthollet, attributed the dissolution of gases in liquids to a form of weak chemical affinity, a selective attraction between the particles of the solvent and the solute. This view implied that solutions were a type of compound, potentially with variable proportions. The alternative perspective, rooted in the corpuscular philosophy of Isaac Newton, conceived of the process as purely mechanical. It imagined gases and liquids composed of ultimate particles, and their mixture of physical intermingling governed by forces of attraction and repulsion. This mechanical philosophy was the intellectual wellspring from which Dalton drew his inspiration. Seeking a model that could account for the precise, quantitative regularities he was beginning to uncover, he was directly engaging with the work of his contemporary, William Henry, who in 1803 had published his own findings on the topic. Henry had established an empirical rule, observing that the mass of a gas absorbed by a liquid is directly proportional to the pressure of that gas. This relationship, now immortalized as Henry's law, provided a crucial piece of empirical data. Dalton, however, sought something more profound than an empirical correlation. He sought a causal, physical explanation grounded in the ultimate constitution of matter itself. Dalton's experimental approach, detailed within the 1805 paper, was characterized by a deceptive simplicity that belied the power of his reasoning. His apparatus consisted of little more than glass vessels, a water trough, and graduated tubes with which he could agitate a fixed volume of water, with a specific gas and measure the amount absorbed through systematic experimentation with a variety of gases, including oxygen, nitrogen, hydrogen, and carbonic acid. He confirmed Henry's general finding regarding the effect of pressure. His crucial innovation, however, came from his experiments with mixtures of gases. From these observations, he formulated what is now known as Dalton's law of partial pressures. He concluded that the total pressure exerted by a mixture of non-reacting gases is equal to the sum of the pressures that each individual gas would exert if it alone occupied the entire volume. This principle was revolutionary. It implied that in a mixture, each gas behaves as if the others were absent, a state of mutual indifference that defied explanation by chemical affinity. To account for this phenomenon, Dalton proposed a bold and counterintuitive physical model. He postulated that the ultimate particles of a given gas repel only particles of their own kind, while they exert no force, neither repulsive nor attractive, upon the particles of a different gas. In his conceptualization, the space between nitrogen particles in the air was a perfect vacuum to the oxygen particles, and vice versa. This static, particulate model, where repulsion was a selective, species-specific force, provided a purely mechanical explanation for why each gas in a mixture acts independently, both in exerting pressure and in dissolving into a liquid. The quantity of a gas absorbed by water, therefore, depended solely on its own partial pressure, a direct consequence of this particulate independence. The true significance of the 1805 paper transcends the mechanics of gas absorption, for it was in explaining the differences in solubility among various gases, Dalton was forced to make his greatest intellectual leap. He observed that under the same conditions of temperature and pressure, water absorbs a far greater volume of carbonic acid than of nitrogen. If the process was purely mechanical, as his model of partial pressures suggested, this difference in solubility must arise from a fundamental, intrinsic property of the gas particles themselves. Dalton proposed that this defining characteristic was their weight. He reasoned that the absorption process involved a balance of forces, the pressure of the gas pushing particles into the liquid versus the repulsive forces between the particles already dissolved. This equilibrium would naturally depend on the size and weight of the particles. This line of reasoning led him to the paper's most momentous inclusion, a first published table of relative atomic weights. Using hydrogen as a standard unit with a weight of 1, Dalton assigned relative weights to the ultimate particles of several elements. Acid, or nitrogen, was given a weight of 4.2 carbon, or carbon, a weight of 4.3 oxygen, a weight of 5.5, and so forth. These values were derived by a masterful synthesis of his absorption data, with the law of definite proportions and the emergent law of multiple proportions, which he himself was formulating from analyses of compounds like methane and ethylene. For instance, knowing water was composed of hydrogen and oxygen, and assuming the simplest combining ratio of 1 particle of each, he could use the bulk weights of the reacting gases to infer the relative weight of their constituent particles. The paper on gas absorption thus became the public debut of a comprehensive atomic theory. It quietly asserted that all matter is composed of indivisible atoms, that atoms of a given element are identical in weight, and that chemical combination occurs in simple, whole number ratios. The act of weighing the atom, even with the primitive accuracy of his first table, transformed it from a philosophical speculation into a quantifiable, scientific entity. The reception of Dalton's work was complex and bifurcated. The law of partial pressures, as a practical and verifiable principle, gained relatively swift acceptance among the scientific community. It provided an invaluable tool for pneumatic chemistry, allowing for the correction of gas volume measurements made over water. The atomic theory, however, with its bold claims about the unseen world and its reliance on the unproven rule of greatest simplicity in combining ratios, sparked considerable controversy. The eminent Berthollet remained this steadfast opponent, his belief in compounds of indefinite composition placing him in direct opposition to the stoichiometric certainty that underpinned Dalton's entire system. There was also the delicate matter of priority with William Henry. While Henry had published the empirical law of solubility first, Dalton's contribution was the profound theoretical framework that explained the law and connected it to a universal theory of matter. The subsequent evolution of chemistry can be read as a century-long dialogue with Dalton's 805 propositions. The Swedish chemist Ernst Jacob Berzelius, recognizing the immense power of Dalton's concept, embarked on a monumental lifelong project to determine accurate atomic weights for all known elements, providing the robust empirical data that Dalton's initial table lacked. The work of Joseph Louis Gay-Lussac on the combining volumes of gases presented an apparent paradox for Dalton's model, a puzzle that was elegantly resolved by Andio Avogadro's brilliant hypothesis distinguishing between atoms and molecules. Later in the century, the development of the kinetic theory of gases by physicists like James Clerk Maxwell and Ludwig Boltzmann would provide a far more sophisticated and dynamic physical basis for the law of partial pressures, replacing Dalton's static, ad hoc model of selective repulsion with a theory grounded in particle velocities and collisions. Yet, this new theory confirmed the correctness of Dalton's law, a testament to the power of his initial insight. In conclusion, On the Absorption of Gases by Water and Other Liquids is a landmark of scientific literature, a work whose modest title disguises its revolutionary ambition and accomplishment. It chronicles a seamless intellectual journey from a specific, empirical puzzle to a theory of cosmic scope. John Dalton's investigation into why different gases dissolve to different extents in water led him to construct a conceptual edifice that would become the very foundation of modern chemistry. His physical model of selective particle repulsion, while ultimately superseded, was the necessary, intellectual scaffold that allowed him to erect the principles of his atomic theory and present the world with a method for quantifying the building blocks of the universe. The paper stands as a powerful illustration of how the rigorous pursuit of a small question can yield an answer of immense proportions. Through meticulous observation and audacious theoretical conjecture, a self-taught philosopher in industrial Manchester transformed chemistry from a largely qualitative art into a precise, quantitative science. After 1905, the material world was re-envisioned. It became a realm governed not by vague affinities or mystical essences, but by the simple, elegant, and powerful arithmetic of the atom. The quiet dissolution of a gas into a beaker of water had revealed the fundamental numeracy of existence itself.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.